So as we said, we have a pair of talks on real-time water resources management, and the first speaker is Matt Bartos. Matt is an assistant professor of civil engineering at the University of Texas at Austin, where his research focuses on developing the next generation of smart urban water systems. Matt will speak about how AI is enabling new science of real-time hydrology.
All right. Well, thank you, everybody, for inviting me. It's an honor to talk here at the National Academies. As David mentioned, my name is Matt Bartos. I'm an assistant professor at the University of Texas at Austin. Today, I'm going to discuss some new directions that AI and machine learning are unlocking within the areas of water resources engineering and hydrology. My goal here is not to give you a comprehensive review of AI in the stormwater sector, but rather to give you a big picture prediction of where the field is moving. So as of 2025, it has become impossible to avoid the question of how AI is going to affect the field of water resources. As Branko mentioned, we have to get on the bus. AI companies have accounted for about 80% of gains in US stocks in 2025. And in the first half of 2025, AI data center build out and spending on information processing equipment has accounted for, by some estimates, a majority of GDP growth. So this level of investment is predicated on the promise that AI will revolutionize productivity across multiple sectors of the economy, ranging from software to medicine and so on. Naturally, the question is for us, how is AI going to change the water sector? And before we can answer this question, we need to acknowledge, as Branko mentioned, that within water resources engineering, AI has actually been around for a long time. Neural networks, the basic technology that powers large language models like ChatGPT, have been used for rainfall prediction since at least 1992. Throughout the late 2010s and early 2020s, there was an explosion of academic literature concerning the application of machine learning and AI methods to hydrology and water resources. And these advances were powered by the release of different open source AI frameworks like PyTorch, TensorFlow, scikit-learn, and so on. So the rise of machine learning and AI in water resources management significantly predates large language models like ChatGPT. This has been going on for a while now. And within stormwater and hydrology, AI applications fall into four major areas. First, the most popular application of machine learning in stormwater hydrology has been the development of data-driven surrogate models. So I would say this probably accounts for something like 60 to 70% of the machine learning literature in hydrology. Conventional physics-based models are often too complex to develop and too slow to simulate for large areas. And as a result, researchers have derived new methods for creating fast, data-driven surrogate models that quickly simulate things like stream flow or flood inundation extent at scales that previously would not have been possible. In addition to simply being faster, data-driven technologies are surprisingly often more accurate than traditional models because they're able to extract new information from observed data that is not captured by existing hydrologic theory. So in particular, machine learning techniques are effective at learning dynamics that are poorly understood or poorly characterized, such as, for instance, subsurface flow of water at the catchment scale, or the influence of human activity on the hydrologic cycle. One poorly understood phenomenon that is particularly important to hydrology is rainfall prediction, which has always been the largest source of uncertainty in hydrologic modeling. In recent years, there have been major advances in prediction of rainfall using machine learning techniques. The GraphCast model, for instance, developed by the Google DeepMind team, outperforms conventional numerical weather prediction models 90% of the time for predicting weather variables at 10-day lead times. And for short-term precipitation forecasting, which is notoriously difficult, AI-based methods like MetNet2 outperform state-of-the-art conventional models, even at relatively long 12-hour lead times. In addition to simply learning patterns from existing data, AI techniques are also opening up entirely new types of sensing by extracting useful information from data sources that previously would have been ignored. So some new modalities of sensing include learning rainfall rates from CCTV camera footage, estimating flood extent from crowdsourced photos and social media posts, and finally, improving rainfall nowcasts by incorporating windshield wiper data from connected vehicles. So finally, AI is not only improving our knowledge of stormwater infrastructure, but also it's providing new tools to change how it operates. And this is something you'll be hearing throughout today's talks. Stormwater systems are now being dynamically controlled using actuated valves, gates, pumps, and so on to mitigate long-standing hazards like combined sewer overflows, flooding, and non-point source pollution. AI is enabling these new control strategies in two ways. First, by providing fast surrogate models that are capable of running in real time. And second, by enabling new complex learning-based strategies for optimization of control schedules, including things like reinforcement learning and Bayesian optimization. So the question is, where is this headed? Are these techniques simply a collection of useful tools? Is this a Swiss Army knife of hydrology, essentially, that's going to save engineers time in performing our conventional duties of modeling, validation, calibration, and design? Or are they leading somewhere entirely new? My thesis for today is that if you look at these different puzzle pieces, we are indeed moving in a new direction. And specifically, AI and machine learning are laying the groundwork for what I call a new field of real-time hydrology, one that is facilitated by fast data-driven models that are capable of being executed in real time at areas of unprecedented size, using better forecasts that can adapt to rapid changes in observed data, using new data sources to gain real-time observability of our previously obscure hydrologic systems, and providing new tools for decision support that are allowing water managers to not only regulate and design stormwater infrastructure, but to operate those systems intelligently. This new mode of hydrology is characterized by the need to make predictions in the face of pervasive uncertainty that existing deterministic methods do not handle well. To tame that uncertainty, it's characterized by the need to fuse multiple data sources together, including the assimilation of sensor data and remote sensing data with models to achieve usable predictions. And finally, it's a mode where the timeliness of the results is just as important as the accuracy. So for the last 5 years, my lab group at the University of Texas at Austin has been exploring this space of real-time hydrology and how machine learning methods can be used to help our water infrastructure operate better. We've shown, for instance, that active control of stormwater basins can be optimized through machine learning techniques to significantly improve contaminant removal while also avoiding floods, even under extreme uncertainty in rainfall forecasts. We've developed real-world stormwater digital twin models for the urban drainage network in Austin, Texas, that combines together a physics-based hydraulic model with a low-cost wireless sensor network. And while low-cost sensors are often difficult to use because they're very noisy and thus water managers don't trust them, we developed a machine learning approach that's capable of detecting and removing sensor faults with almost 100% accuracy, which opens the door to ubiquitous low-cost monitoring and modeling of urban stormwater systems. And on the water quality front, we've also developed real-time digital twin models of nutrient transport and harmful algal blooms for large river networks. And crucially, by fusing sensor data into a physically based model, we found that we can outperform traditional process models in the prediction of algal growth. And this opens the door to potentially controlling river reservoir systems to mitigate algal blooms, which can be hazardous to human health. However, I'd like to focus on one project in particular where the outcomes of the project not only resulted in real-world impact, but where machine learning was also necessary to the success of the project. And this project is the flood assessment system for the Texas Department of Transportation, which Dr. David Maidman actually presented here at the National Academies last year. So this is a major project that aims to predict in real time the probability of flooding at every single roadway in the state of Texas, which is an absurdly ambitious goal. Texas has the highest number of vehicle-related flood fatalities in the US. From 1959 to 2019, there were roughly 6,500 flood fatalities in the US. About 1,000 of those were in Texas, and about 570 of those were vehicle-related, meaning that about 1 in every 11 or 12 flood fatalities in the US was a vehicle-related flood fatality in Texas. So to address this problem, the Texas Department of Transportation launched its largest ever research project with the goal of developing a statewide emergency response system that would allow emergency operators to detect flooded roadways in real time and dispatch maintenance crews to close roadways before accidents occurred. The outcome of this project is a functional flood alert system for the entire state of Texas that allows operators to inspect individual bridges in real time and view the probability of flooding over an 18-hour forecast window. So how was machine learning instrumental to the success of this project? First, to realize a system of this scale, we needed a fast hydrologic model that covered the entire state of Texas. Developing a traditional physics-based hydraulic model for the entire state of Texas was out of the question. So instead, we developed a simplified linear model that used only a few key parameters related to the flood wave speed and diffusivity of the wave in the channel network. We then applied a machine learning approach called expectation maximization to learn the parameters that best match observed data. And the result was a fast hydrologic model that was capable of simulating 18-hour discharge forecasts for all of Texas in less than 3 seconds. The second major hurdle was ensuring that our forecasts of flooding were trustworthy and that they accorded with our best knowledge of the system. So to illustrate, let me show you what happens when you try to predict real-time flooding using just a model by itself. So this diagram shows a real overtopping event in the New Year Creek watershed near central Texas, kind of near hill country. The black line here shows the actual water level as measured by USGS stream gauge, discharge. It shows the actual discharge as measured by a USGS stream gauge at the outlet. And right upstream of this USGS gauge, there is a low-lying roadway that overtops whenever the discharge in the stream goes above this blue line. The red line shows the most recent forecast produced by the National Water Model, which is a water model that runs in real time. This is produced by the National Water Center. It produces real-time forecasts for every river reach within the US. So this is kind of like our national numerical weather prediction model for hydrology. So it estimates stream flow in real time at every reach. So this red line here is the continuous forecast, the most recent forecast produced by the National Water Model. So a real overtopping event occurred on May 15th and May 16th of 2023. However, the model forecast completely missed the 2 peaks and worse, introduced 5 different false alarms. So that's not ideal. To fix this problem, we applied a machine learning technique called Kalman filtering that fuses sensor data into the model that I described before. Essentially, what this is doing is it's taking the sensor data along with some estimate of the uncertainty of the sensor data, it's taking the model along with some estimate of the uncertainty of the model, and it's fusing those together in an optimal way. The result is essentially a correction to the runoff field that makes the model output accord with the observed stream flow while still respecting the model dynamics. And as a result, the forecasts are significantly improved. Here, the gray area is the observed discharge from the USGS gauge. The red lines are the successive forecasts produced by the National Water Model, and the blue line is the result of our data fusion approach. And you can see that the forecasts, the 1-hour forecasts, are now very close to the observed stream flow. Validating this approach over a two large river basins in Texas, we find that this sensor fusion approach significantly improves forecasts at all lead times compared to the existing best estimate produced by the National Water Model. So in summary, I believe that AI and machine learning are enabling a new field of real-time hydrology. And crucially, I think that this is not a solution looking for a problem. Rather, the application of machine learning techniques has grown organically out of the need to make real-time predictions under substantial uncertainty in models and forecasts. So these needs have naturally led to the development of techniques for building fast models that run at scale and fusing multiple data sources together to ensure that we're getting timely and accurate predictions. Moving forward, I think that while machine learning techniques are really exciting, I believe that they should fundamentally supplement rather than replace our existing hydrologic domain knowledge. I think there's a need for more research that integrates machine learning techniques with our domain knowledge that we've developed over the years. And as we grapple with how AI is going to change the future, I think it's important to look back in the past and see how these techniques have been used to achieve results in hydrology. So thank you for your time, and I'll take any questions.